Talking about acids and bases, and last time I believe we got into some weak bases. And remember, sort of weak base problems are pretty much like weak acid problems because they are weak bases. They are in equilibrium. They do require an ice table. Typically, for example, like ammonia, which is a weak base, you again usually do want to put kind of the water in the equation, and it's going to accept the H plus there from water. Water is going to act as an acid in this particular case. And the result of that is you'll make NH4 plus and a little hydroxide action. And again, that is what makes it a base. Usually we will ice table this guy up. We will solve for X. Remember though, when you're doing bases, X will pretty much equal the hydroxide concentration. So once again, you do have to get the POH first and then to the pH in that case. Again, you can solve it any way that we've solved equilibrium problems before. You can make the assumption, you can quadratic it. You usually will not have too much probably perfect squares on these type of things, but those would be probably one of your two options. We talked about salts at the end there. And remember, there's three different types of salts. And salts do derive from really the reaction of an acid and a base. Again, we'll usually produce salt and water. And the sort of origin, if you will, of where that salt comes from, the acid and the base, really determines, what's going to happen in terms of will it continue to react. And that's really what we're looking at here. You can have salts that are relatively strong in the sense that they will continue to react with water and will either produce hydroxide or will produce H3O plus and have an effect on the pH. Remember, it is the opposite relationship we talked about. So really, if there's anything that comes from a weak acid or a weak base, those salts will go through hydrolysis, which is, again, that reaction with water. If it comes from something that's a strong acid or strong base, it will not go through hydrolysis. It's considered relatively weak, and that's how you get a neutral salt that should have a pH of 7. Again, if you took something like sodium chloride, as we talked about, most likely came from sodium hydroxide and hydrochloric acid, both strong acid and a strong base. Both of those salts are parts of the salt, which is the sodium ion and the chloride ion. Neither one of them will go through hydrolysis, and the pH here should be 7. Now, it is possible, again, to have a basic salt and something like sodium acetate is an example of that. When sodium acetate goes for a swim, it's going to basically break apart into sodium ions and some acetate ions. This most likely came from like sodium hydroxide and acetic acid. Sodium hydroxide being a strong base, again, means that the sodium ion here is not really of interest as it is a neutral salt. But our acetate here did come from acetic acid, which is a weak acid. So this acetate will continue to react with water. And as we talked about before, if you sort of identify where it came from, so it came from an acid, which means the acetate here will act as a base when it reacts with water. Again, a conjugate base, basically. And it will actually accept that H plus. The result of that there is you will always make, as we talked about, where it came from, acetic acid, and in this case, we are going to get a hydroxide being made, which is why the solution should be basic. It is also, as we talked about, if you had to do a calculation, which would be an ice table in this case, you would want to make sure you're using the correct K value, right? In this case, I should use what K value? A KB, right? Because we have hydroxide there on the product side, so we should be using a KB value. Remember that they very often don't give you the right one in these problems, so that is where our Ka times KB relationship equals Kw will allow you to convert to the one that you actually need. And there's also acidic salts, and acidic salts like ammonia Actually, ammonium hydroxide or ammonium chloride would work. Ammonium chloride here. Do that. Get rid of the plus. So that will get us NH4 plus and Cl minus. Cl minus from hydrochloric acid, not going to be important, but that NH4 plus will go through hydrolysis and react with water. It does come from ammonia, which is a base, which means when this reacts with water, it will react as an acid, and it's actually going to donate the H plus over to the water. The result of that in the terms of pH will mean you will produce some H3O plus, and obviously you will also produce where it came from, the NH3 as well. And in this case, we would expect the solution to be acidic because of that. And if we're doing a calculation, which again is a nice table, we would want to use the Ka value. So people oftentimes struggle with which K value they should use in these situations. You just want to keep it simple. If you have, again, H plus or H3O plus on the product side, you should be using a Ka value in your calculation. And if you have hydroxide on the product side, again, you should be using that Kb value. And the importance of, again, being able to write these equations correctly, well, again, as we talked about, help you with the math part of it. There's a second way that you could get an acidic salt, which is basically a metal, like a transition metal that has like a +2, +3 type charge, where one of the waters sort of that's surrounding that ion in solution will give up an H plus to another water and make H3O plus. Any questions on any of that stuff we talked about last time? All right. Now let's do some calculations perhaps with some salts. We're looking for what is the pH of a 0.45 molar potassium, about where the salt came from. So that's potassium chloride, which is a strong electrolyte like most salts are, and it will break up into K plus and Cl minus. So what we want to think about is there any part of this salt that will basically go through hydrolysis, will continue to react with water? How about potassium? Do I need to worry about that guy? I don't remember group 1 and group 2 where we really find our strong bases come from. Are not going to go through hydrolysis, so that's not an issue. How about the chloride? The chloride came from probably what acid? HCl. HCl is what type of acid? Yeah, which means its conjugate partner, Cl minus, is weak, opposite, yeah? Will not go through hydrolysis either, yeah? Those are two neutral guys. pH is 7, no calculation required, yes, in this case. Any questions on that one there? So again, both of these salts won't go through hydrolysis or shouldn't go through hydrolysis, as they both really originate from two strong things, a strong acid and a strong base. And we would expect really no reaction with water, and we will have a pH of 7. Question on that one there. All right, let's try one that does have a calculation. Let's try. Okay, so let's take a look and see. So once again, we do have a salt given to us, and that is sodium fluoride. Remember, a salt's going to pretty much 100% dissociate into ions in solution. So it'll be floating around there. These guys on the right-hand side. So once again, you want to sort of decide, you know, what's going to happen in this case. So again, we look at sodium. And as we talked about a number of times at this point, it is group number 1 and really probably came from sodium hydroxide, which means we really don't have to worry about that going through hydrolysis. The F minus here most likely came from, yeah, and again, there's a lot of pieces of information in this problem which is helpful for you. One of those being right there, HF is given to you. You're also given a Ka value for that HF, so automatically you know it is what type of acid? It is a weak acid, right? And because it's a weak acid and this guy came from it, it will go through hydrolysis, right? So it's not that opposite relationship. We also know that because this guy here is a weak acid and this guy came from it, his partner there the HF partner, which is the F minus, would be a conjugate base. So now we know basically it's going to act as a base when it reacts with water. Also, just logic tells us it cannot give an H it doesn't have, so it's got to go base-wise there since it doesn't have the H to give. So now we have really half of our reaction sort of set up. We know that we're going to have our F minus plus our water in this case. We know it's going to act as a base, which means the water is actually going to send the H plus over there to the HF, or to the F minus. Remember that when a salt reacts with water in a hydrolysis reaction, it always makes where it came from, which means that's quite helpful as well because that's what goes on the other side, basically, also given to you, which is HF. And we will produce hydroxide in this particular case as water gives away its H plus in this case. First off, any question on the reaction there? Without doing the calculation, when it's all said and done, my pH should be acidic, basic, or neutral. It should definitely be basic because we have OH minus happening, right? So let's do our ice table here. We're going to put our 0.3 molar. And again, I know that is the concentration of my fluoride because it's a 1-to-1 relationship between those. So the concentration of the fluoride is 0.3 molar as well. In case you ever needed it, which you don't in this problem, but the sodium ion concentration would also be 0.3 molar, but you don't really need it for this particular problem. We're going to go a little 0-0 action. We're going to go minus X plus X plus X. A little 0.3 minus X, X, and X. This, like normal, is going to go into our K expression, which is our products, our HF, our OH minus, divided by our F minus. By the way, this is a K, A, B, C, D, E, F, G. Could be a G, you never know. This should be a K. Should be a KB also because we have our hydroxide, not a Ka, which means the nice Ka value they gave us is not really the one we need, right? We actually need to convert it to the Kb value in this case. So again, getting that equation correctly, when you see it, should tell you you should get a basic pH and you need to use the Kb value in this particular case. So again, I can't stress how important it is to be able to get those equations correctly. So the Kb in this case will be our Kw divided by the Ka, and that comes from Kw equals Ka times the Kb. Remember, Kw is still the same number we used previously, which would be 1 times 10 to the minus 14 divided by our 7.2 times 10 to the minus 4. Attempt it with one of these calculators. I'm not sure where my real calculator went. Maybe I'll find it sometime this week. We'll see. Also lost some goggles as well. I'm not sure. I'm hoping to find where I parked later. It'll be all right. 7.2 minus 4. All right. So I think we got for a KB in this case, I don't know, we'll go 1.4 times 10 to the minus 11. Sounds good. All right. So again, we want to use that as 1.4 times 10 to the minus 11. We're now going to put our X values into this. So that'll give us X squared divided by 0.3 minus X equals 1.4 times 10 to the minus 11. Maybe I'll flop the page there so it could write up on top, maybe. But let me do so. Maybe. There we go. Oh, no, it came back. Look at that. All right. All right, so we have X squared 0.3 minus X equals 1.4 times 10 to the minus 11. Obviously, that's a small K value, so why not go for the assumption here and assume X is equal to 0? It's going to give us S squared over 0.3 equals 1.4 times 10 to the minus 11. Reminder, obviously, you can't get rid of all the X's. So I'm going to times the 0.3 to the other side. And then I'm going to do a little square root action, hopefully, on this calculator. All right, so I'm going to multiply that followed by a square root. And that's going to give me an X of, a lot of zeros count. 1, 2, 3, 4, 5, 2, 0, 4, 1. I went quick, hoping the best. 1, 2, 3. All right. So we do need to check it. So we'll divide it by 0.3. We'll times it by 100. And I don't even think you're at 100% or 1%. So the check is good in this case. I think it's like 0.00 something percent. That would mean in this case, if we go back to obviously to our table, the X again here does not equal the H plus concentration, but it does equal the hydroxide concentration. So this would be our hydroxide concentration. We then could go into our POH minus the log of what we got going on there. And let's see, negative log. I'll go with this one. That calculator, I can't even see the buttons. All right, so 5.69. And again, if by some chance you were confused and thought that this was the pH, it should not make sense to you, obviously, because that's less than 7. And obviously, we're dealing with a basic solution. So our pH in this case would then be 14 minus our 5.69er and a little 14 action, 8.31, which is a basic pH and would make more sense. Question on any of those steps. So really, just a basic equilibrium type problem. The key is, again, getting that equation correctly and making sure that you can see what's on the product side, because that will hopefully also help you understand that you want to make sure you're using the right K value, which again is a super common error people will do on this. Yeah. Any questions on that one? All right, let's try another one here. The pH, what is the pH here of a 0.75 sodium cyanide solution? Okay, so once again, let's take a look. We got another salt, so we're going to break it apart and again try to identify if anybody here is going to go through hydrolysis. So hopefully at this point we know sodium will not, again for the same reasons we talked about previously. How about the CN minus? CN minus will, because again, some of that piece of information given to you in this problem happens to be HCN is there. HCN is obviously a weak acid as a Ka value, which means if this is a weak acid, the CN minus would be its conjugate base and be relatively strong. And once again, that is also how it's going to react with water in this case, right? It's going to act as a base. So that's where we want to start. We're going to get our hydrolysis reaction going. Again, here, really, it does not have any option other than really to accept the H plus. The result of that, once again, if you're not sure, will always form where it came from. So you also have the formula of that right there in the problem as well, that a lot of people just sort of overlook. And we have a little hydroxide action happening here again. So once again here, without even doing the calculation, we should know when we're all done, our pH once again should be basic, yeah. We also know when I do my calculation, I should be using a KB as well, right? And this guy again should be basic. All right, so popping in our initial concentration here, 0.75. Once again, it is a 1-to-1 relationship between those, so the concentration is the same for both of them. And again, we will have zeros, minus X, plus X, plus X. Coming down here, 0.75 minus X, X, and X. Once again, we'll go into our KB, which is our HCN, our hydroxide, and our CN minus. We do need to calculate our KB value. So our KB value in this case going to be our KW, which is 1 times 10 to the minus 14, divided by 6.2 times 10 to the minus 10. Give it a try here on this one, let's say. Yeah. So that will get us a KB value here, 1.6 times 10 to the minus 5, I believe. 1, 2, 3, 4, 5 there. All right, so now that we got that, we can put our values in. So maybe I'll flop a page here so I could maybe do it above here. So we got x squared divided by 0.75 minus x equals 1.6 times 10 to the minus 5. Once again, here we're going to assume that x is equal to 0. That will basically get rid of that guy right there. We're then going to multiply, followed by a square root after that. And if we do that times 0.75, a little square root action, going to give us an x value here of 0.00348. We do want to check it to make sure it's all okay. And if you do that by again dividing by 0.75 times by 100, check is good. It's like 0.4%, so everything's good there. Let's say in a lot of cases, you're probably going to be okay on these hydrolysis ones in terms of the assumption. That again, if we go back to our table, once again is not the H plus concentration, but again, it is the OH minus concentration from our table. And that means we'll go into our POH minus the log there of 0.00348, a little 2.46. Then subtracting our 14 there to get us to our pH, which is what we're looking for. 1154, which definitely is a basic pH in this case. Any questions on that there? Let's try one more. I'll just make up. Why not? See how we do. What is the pH of a 0.55 molar ammonium chloride solution? The Kb of NH3 is 1.8 times 10 to the minus 5. All right, go for break apart, perhaps, into ammonium and some chloride. Once again, we want to kind of think about what's going on. We know, hopefully from previously, we could really not worry about the chloride, again, because it most likely came from HCl, which is a strong acid, which means it will not go through hydrolysis. The NH4 plus that hopefully you realize perhaps came from this guy right here will go through hydrolysis. So we have a Kb value given to us for NH3, which I know is a weak base because it would not have a Kb value if it wasn't. Because it's a weak base, we know that this would be technically as conjugate acid, right? It's kind of partner, if you will. And because of that, it will be relatively strong and will go through hydrolysis. So that would be our reaction we want to write, which is our NH4 plus our water. Once again, by also kind of thinking about that that's the base and the partner over here is the acid, we will once again know how it should react with water. In this case, it's going to act as a Bronsted acid, which means it is actually going to be the one that is donating the H plus over in this case. And the result of that is, as we talked about, it will always make where it came from, which again just happens to be in the problem as well, which is NH3. When that water gains the H plus, it will become H3O plus in this particular case. Any questions on the reaction there? That also answers a lot of questions for us in terms of what we should expect to happen at the end of our calculation. We should expect it to be what type of pH? Acidic, basic, or neutral? Should be acidic. We also should now know we should use what K value when we use this? Yeah, again, we do need a Ka value because we do have that H3O plus there on the product side. So we'll put our ice table here together, 0.55, see how we did with my made up numbers. We'll see here. Change going to be minus x plus x plus x, going to get us an equilibrium 0.55 minus x, and x. Once again, we're going to go a little Ka action here because we did produce an H3O plus. So our products here divided by our reactants. And obviously we will need the Ka value here. So you do a little Ka will be Kw divided by the Kb, a little 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. Gonna get you like a 5.6 times 10 to the minus 10, perhaps. Yeah. Gonna put that in as our Ka value. We now can put our x's and stuff in here. So x squared over 0.55 minus x equals 5.6 times 10 to the minus 10. Here, obviously, we're going to assume x is equal to 0. That will basically get us still this right here, an x squared divided by 0.55 equals 5.6 times 10 to the minus 10. Like before, we're going to multiply followed by a square root. And I'll try this one. Maybe it'll wake up for a second. All right, my batteries are low. I understand that. Yeah, 5.6 to the minus 10 times 0.55. A little square root action before the batteries die. Going to get us a x value here of 1.75 times 10 to the minus 5. Clearly, this one's in scientific notation, not scale zeros. We do want to check it. So what's going to here, we're going to divide by 0.55 times it by 100% just to check it. But I think we're probably going to be good here. 0.55 times 100. Again, 0.003%. So the check here is good. Remember, though, in this case, because we wrote the equation reaction correctly, we see that the x in this case actually is the H plus concentration, right? So that's going to equal our H3O plus concentration, which means unlike the last one, we could actually just go right into our pH equation here, minus the log of 1.75 times 10 to the minus 5. Let's see how I did. Not too bad, hopefully. Minus, you see, it dies right when you want the final answer. Let's switch over to this calculator, which you can't really hold because it doesn't like it. All right. All right, I'll just do it in my head. All right, the pH is 4.75. What do you think? There you go. All right. So pH there, 4.75, which is, or 7.6, depending if you round. But 4.75, which is obviously an acidic pH, which is what we would expect in this case. Any questions on pH of salts? Yeah. So again, like I said, hardest part for a lot of people is the writing the equation part. And the second part that most people screw up on, again, is using the wrong K value, okay? So you got to understand what's going on so that you get the right value to use. Now, before we move on with our salts here, this is a prettier picture of that aluminum thing I drew the other day, where, again, it's another way we could get an acidic salt. And as you can see, one of the waters attached is just going to kind of give up an H plus there. It's going to form our H3O plus, and that's what will make it basically acidic. Now, what happens, though, if you had, say, a salt such as, say, ammonium nitrite? So if I had a salt such as ammonium nitrite, that would break apart into these two. So we know from our last problem that that guy will go through hydrolysis. Yeah. How about this guy? Will this guy go through hydrolysis? What acid do we think that came from? Close. It came from HNO2, which is nitrous acid, which is actually a weak acid. By the way, I know it's a weak acid because it's not one of the 6 strong ones that we remembered, right? So again, a good idea to remember those 6, and you could do like a process of elimination to help you. Which means because it actually is a weak acid, this guy as well is on the hydrolysis route as well and will go through hydrolysis. So you can have a salt that both of them will go through hydrolysis. Nobody wants to do that calculation because this kind of long is scary and all that kind of things. So it is definitely possible. So in a situation like this, if you find yourself with a salt where actually both will go through hydrolysis, What you actually want to do is compare the Ka value and the Kb value and see which one is larger. And whichever one is larger will pretty much be the calculation you should do. So if you have a salt and the Kb for the anion is larger than the Ka value for the cation, then you really should do the basic calculation with the Kb and just do the Kb, ignore the other guy and the Ka sort of calculation. If you do the Kb comparison for the anion and the Ka is larger, then it will be acidic and you should just do the Ka calculation. And if you happen to have a Kb and a Ka that are pretty much equal to each other, go with a pH of 7, right? Neutral, right, in that case. So you can definitely have a salt that can go both ways. But again, if you have to sort of do it, you want to compare the Ka to Kb. And again, whichever one is larger, that's pretty much the calculation you should do. So obviously, if the Kb was larger, then perhaps you should end up with a basic, obviously, pH. And if the Ka is larger, you should end up with acidic pH. Any questions on that there? Okay. So again, although most of the examples that you come across and most of the ones that we did, only one part of the salt will go through hydrolysis, it is definitely possible that you could have both parts actually go through it. Any questions on that there? Okay. Now let's talk a little bit about oxides. Good talk. Let's go back and try that again. All right. So oxides are obviously elements that have oxygen in it. And these elements, when you react it with water, will produce either like bases or acids. So as we've been talking about, really group 1 and group 2 on the periodic tables where we have a lot of our strong bases come from. So if you react something, let's say like sodium oxide there, with some water, you'll get some sodium hydroxide and you'll make a lot of bases. So on the left-hand side there in group 1 and 2 are pretty much what are referred to as being basic oxides. They tend to produce bases when they sort of react. On the sort of non-metal side over here is where we get a lot of our acids from when they react with water. So for example, like CO2 there, right? And you react it with a little bit of water, maybe get a little H2CO3, carbonic acid, as a result of that. So the guys on the kind of right-hand side there of the periodic table are considered acid oxides because, again, when they react with water, they will produce acids. We have some orange ones here. Orange are amphoteric. And amphoteric, a reminder again, is a substance that can act as an acid or a base. So those guys can kind of go either way in that situation. Any questions on that there? Now, we talked about a couple definitions of an acid and a base. We talked about the Arrhenius definition, where an acid produces H plus in solution, or a base produces OH minus in solution. We talked about the Bronsted-Lowry definition of an acid and a base, which is, again, an acid is a proton donor, give away an H plus. The base will accept an H plus. Our friend Lewis was felt left out. So he wanted a definition of an acid or a base. When we think about a guy named Lewis, we think about Lewis structures. And we draw Lewis structures with, what are in Lewis structures? Electrons, yeah. So oddly enough, his definition of an acid and a base involves electrons. So the Lewis definition of an acid and a base, not filled in for me, so I'm going to try to remember here. So a Lewis acid is a substance that will actually accept a pair of electrons. A Lewis base is a substance that will donate a pair of electrons. So a Lewis acid and base involves electron pairs being donated and accepted. While again, a Bronsted-Lowry definition, obviously, of an acid and base is one that involves a proton, H plus, being either donated or accepted. Those two definitions will both give you the same answer in terms of, is this thing an acid or a base? It's just sort of a different way of looking at it. We will see Lewis bases and Lewis acids later on as well when we get into transition metal chemistry and coordination compounds. But it is a definition for an acid and base. So if we take a look at this one here, in this case, the hydroxide is going to donate a pair of electrons over there to the H plus, and that would make our hydroxide the base. And this guy would be our acid. Now, ammonia has a pair of electrons here that it can donate over, and that would make this the Lewis base and this our Lewis acid. Now, the pair of electrons that somebody's going to donate does need to be available to donate. And the places where you get people that have electrons to donate are a couple places, like ammonia, like also water as well. They are polar molecules that have unpaired electrons on it, right? So here it has unpaired electrons. Water's also a Lewis base. It has those unpaired electrons on the oxygen, and it's polar. That makes it a really good Lewis base. The other things that are pretty good Lewis bases are things that have like a negative charge. Yeah. How do you get a negative charge? Typically, you've done what to get a negative charge? You've gained electrons, right? That's how you become more negative, right? You gain some negative electrons. So you have some electrons to give in that case, right? And something like, for example, Cl minus, right? It's got some extra electrons perhaps to give. And that's another really good Lewis base in that situation. Now, one of the good definitions of Lewis acid and base is the idea that, by the way, before we look at this here, our basic Bronsted-Lowry definition also gives us the same answer. This would be our proton being donated, which means that's the acid, and that guy's going to accept the proton, so that's the base. Same thing here. Proton being donated, he's going to accept it, making him the base and not the acid. Now, one of the nice applications of a Lewis acid and base is you actually don't even need a proton to be involved for you to apply sort of the Lewis acid and base. Like in this situation, there is no H plus being transferred at all in this situation. It is simply our electrons coming from our ammonia to our boron, making again our ammonia our base, our boron our acid. Boron is one of those incomplete octets, which means it's electron deficient, right? It is perfectly happy with 6 electrons, and it has room to accept some because it has less than the octet rule in that case. So you can actually apply acid-base chemistry to things that don't involve protons being donated and accepted, like the classic sort of Bronsted-Lowry definition. And that, as we will see in sort of our coordination complex ion chapter, is how we sort of look at that sort of interaction of complex ions and how they're formed. Question on Lewis acids or bases. Okay. The last thing we're going to talk about in this chapter is what happens when we have polyprotic acids and how we go about sort of doing those calculations. There are, as we probably talked about, if you have like an HA, that is going to give away or release 1 hydrogen, and A minus, that again is going to be a monoprotic acid, right? And again, something like HCl would be an example of that. If you have a diprotic acid, which has essentially 2 hydrogens to give, it would ultimately, at the end of the road, give away 2 hydrogens, and we'll end up with something like this. This obviously is something like sulfuric acid is an example of that. And if you have, and again, that is a diprotic acid, di meaning it has 2 protons to give. You could have a triprotic acid, which ultimately, when the journey is done there for them, will give away 3 hydrogens. And we'll have a -3 charge overall here. And again, something like phosphoric acid would be an example. That is a triprotic acid. Now, it's really important to remember or note that actually the hydrogens in a diprotic acid or a triprotic acid actually come off one at a time. They don't all just drop off at once. So for example here, if we took something like phosphoric acid, the very first thing, phosphoric acid is a weak acid. Very first thing that would happen is this phosphoric acid would give away one hydrogen only, and that would give us H2PO4 minus. And there actually, it will set up an equilibrium, and there is an equilibrium constant just for this step, which is sometimes referred to as the Ka1 value for the first hydrogen that pops off. Then what will happen is that guy that has lost one hydrogen will then decide, hey, why don't we just pop off the second hydrogen here for fun? And we will end up with HPO4 2 minus. And there's also an equilibrium for that, which is on a table known as the Ka2 value for the second hydrogen that pops off. And lastly here, this guy that has already lost a couple of hydrogens at this point, we'll decide why not give away the third one because it's free today. And we will make PO4 3 minus, and that would be our Ka3. So it is actually a stepwise dissociation or ionization of this acid. It will release each of those hydrogens one at a time. Yes, sir. That was my next question. Is it easier to remove the first hydrogen or the second one? Which one's easier? It is much, much easier to release the first hydrogen than it is the second. And it's even harder to release the second after you release that first one to get to the third. So, and the reason for that is obviously here, right? When we started, we are neutral, right? Which means when we release that first hydrogen, we become negative, and now you want to pull off something that's positive, so it makes it a little more difficult. Then when you pulled off that one, you're now doubly negative there, makes it doubly harder. Not really doubly, but it makes it harder in essence as well. So it does get harder and harder every time you want to take off a K value or an H plus, and that is reflected in these values. The Ka value would be a larger value than the Ka2, then the Ka3. It gets smaller and smaller as you go from Ka1 to Ka2, Ka3. And that is because it gets harder, which means this value gets smaller. And when it gets smaller, I mainly have reactants or products. If I have a small K value, I should mainly have reactants, yeah, which means it's going to stay together. This guy gets even smaller, which means it's more going to stay together. Not a lot of it's going to come off. So it does come off in a stepwise fashion. Now, you may have seen it maybe in Chem 200A or something like that, where it just shows them all coming off at once. What you're really looking at that point is adding all these guys together, basically. So if you add all these reactions together, you will have that cancel opposite sides, that will cancel opposite sides, and you end up with the overall reaction that most people look at and just think, 1, 2, 3, all three of them just drop off at once, and you make phosphate here. But again, what you're seeing when you look at this reaction is really the end result of everybody together, all of them coming off. But it does happen in a stepwise sort of fashion. And if we look at this Ka values here, whoops, come here, there it is. Here is phosphoric acid. You can see the first one's to the -3. Next one, as you can see there, is to the -8, gets much smaller. By the time you get to that third hydrogen trying to come off, it's to the -13, so it's very, very small. So again, what that shows is it gets harder and harder every time you remove a hydrogen to keep doing that. You can see it for our diprotic acids as well. As I mentioned before, probably the only strong acid you'll see on the table with a Ka value is sulfuric acid. It's really not a value, it just says large, which is not very helpful for calculations. And it's only really on the table for the guy that comes off the second hydrogen, basically is why it's on the table, but it is considered a strong acid. So how do we do problems that involve diprotic acids, triprotic acids, if we want to calculate things? Let's go through one here together, and I'll come back to this in just a second. So let's say we had a 5 molar solution of phosphoric acid, and we pretty much wanted to know everybody's concentration that's in the solution, and we also want to know the pH. So The first thing that's going to happen, we'll use our Ka1, our Ka2, and our Ka3. The first thing that's going to happen is we are going to have our phosphoric acid, as we just saw in the previous slide. It's going to drop off one of those H pluses, and it will make H2PO4 minus. And again, that is going to be our Ka1 value here that we get from the table. And we will do an ice table because it is a weak acid. So we will have 5 molar of it. We got 0 of this guy and 0 of this guy. Change will be minus X plus X plus X. That means at equilibrium, we have 5 minus X, X, and X. Any questions on the table so far? This will go into our Ka1 expression, which is the products H plus HPO4, H2PO4 minus, divided by our H3PO4. Putting in our values there, it's going to give us x squared over 5 minus x equals our Ka1 value, 7.5 times 10 to the minus 3. I'm going to assume that x is equal to 0 in this case, and that will give me x squared divided by 5 equals 7.5 times 10 to the minus 3. So that's going to get me here 5 times 7.5 to the minus 3. I'm going to bang it, and then, hey, that works. Square root of that there. And that's going to give me an x value. Again, we are multiplying, then square rooting. X value of 0.194. We do want to check it. So we're going to divide it by 5, times it by 100. And I think we will be okay because I did not want to do the quadratic. So it's 3.8%. Maybe I changed the original concentration from 1 molar where you were bad shape there. So check's good here. Thank goodness. All right. So what that means is off of this first table, we actually have a lot of information given to us. We just calculated, obviously, as we can see, the H plus concentration is going to be 0.194 molar. We also have the concentration of H2PO4 minus, which is 0.194 molar. We also can get the concentration of our phosphoric acid at equilibrium as well. And that's going to go 5 minus 0.194. That's going to give us, we'll call it H3PO4, 4.81 molar. So in terms of what we're looking for, we've now calculated that concentration. We got the H plus going. We got this guy's concentration. We do want this guy's concentration as well. So that's going to require us to go to the second hydrogen coming off. So that is what we're going to do. So let me flip a page here. Maybe it'll let me do it. Maybe, there we go. So we're going to go with our second hydrogen that's going to come off, H2PO4 minus, is going to drop the next hydrogen, and we will have HPO4 2 minus made. That is going to be our Ka2 value. So we're going to do an ice table, and we want to also look at what we just did, which is, in this case, do we have any of this now at this point? And we do. It is the equilibrium concentration that we got from the first table, and the first hydrogen coming off will now be our initial concentration. By the way, we also have some H plus there as well from the first H that came off as well. So we do have some initial concentrations. We have 0.194. We also here 0.194 for our H plus, and we have 0 there. And again, those are our equilibrium concentrations from the first hydrogen. Change is going to be minus X, not minus X, plus X, plus X. going to give us 0.194 minus x, 0.194. Remember, this is plus x and x. This is going to go into our Ka2 expression of H plus times HPO4 2 minus divided by H2PO4 minus. And that's going to equal our Ka2 value of 6.2 times 10 to the minus 8. We're going to put in our values here, which will give us 0.194 plus x, divided by 0.194 minus x is equal to 6.2 times 10 to the minus 8. Why not assume x is equal to 0, you ask? And I agree with you. Let's do that. Not equal to 6, maybe equal to 0 would be good. And that's going to get us 0.194 times x divided by 0.194 equals 6.2 times 10 to the minus 8. I think I could do this math without the calculator. That's probably good at this point. So those are going to cancel. And that's going to give us an x value of 6.2 times 10 to the minus 8. We still should check it. So we'll take our 6.2 times 10 to the minus 8. We'll divide it by 0.194. We'll times it by 100. And we're not even near 0.1%. So the check here is good. Yeah. At this point, we now have another answer we were looking for, which is the concentration of this guy. So the concentration of our HPO4 2 minus is equal to x, which would be 6.2 times 10 to the minus 8 molar. What happens when I put that 6.2 times 10 to the minus 8 in for x in each of these locations? Does the number change? It does not. You can trust me. You can do it. You have a calculator, it probably works. So you can put that number in. So take 0.194 plus 6.2 times 10 to the minus 8. You got 0.194 still here staring at you probably on your calculator. So it does not change all that much. So those concentrations are still hanging out the same, both of those from where they started. And that is a result of it not breaking apart as much, right, as we saw on the first one. Any questions on that one there? Now, that gave us this guy's concentration. Unfortunately, in this question here, we are looking for phosphate's concentration as well. And the only way to get the phosphate is we got to drop one more hydrogen out the door here. So we're going to drop one more hydrogen here, which will require us to do our third hydrogen. So our HPO4 2 minus will lose its hydrogen and make phosphate here, PO4 3 minus. That is going to be our Ka3 value, which was 4.8 times 10 to the minus 13. Once again, from the previous table, we have some initial concentrations, which are equilibrium concentrations. So it was 6.2 times 10 to the minus 8, I think is what we got for that guy on the previous page. Do we still have H plus at this point? We still do, right? It's still that 0.194 number, and that is 0 at that point. Change is going to be minus x plus x plus x, going to get us 6.2 times 10 to the minus 8 minus x, 0.194 plus x, and x. This is going to go into our Ka3 expression, which is our products, divided by our reactants. And that will equal 4.8 times 10 to the minus 13. All right, here we go. 0.194 plus x times x divided by 6.2 times 10 to the minus 8 minus x. We've been good on the assumptions so far, so why stop now? X is equal to 0 in this case. That's going to give us basically 0.194 times x divided by 6.2 times 10 to the minus 8 equals 4.8 times 10 to the minus 13. Gonna multiply and then divide what we got going on there, right? So we're gonna take 4.8 times 10 to the minus 13. We're gonna multiply it by 6.2 to the minus 8. We're then going to divide it by 0.194. And that is going to get us Yeah, dare I say, an X value of 1.53 times 10 to the minus 19, I think is what my calculator says. One more time, we're going to check it here. We'll divide it by 0.194 just for fun and times it by 100, and we're good. We're nowhere even near being bad. Check is good. That means the phosphate concentration should be that number right there, 1.5. I'll round it to the minus 19 molar in this case. What happens when we put that number back into these X's? Does the numbers change? They do not, right? Because it's a super small number, so they'll remain the same. So in this case, we could go through each of the hydrogens coming off, the stepwise dissociation. We really had to go all the way down here to the third one for the phosphate only. The reason we didn't really necessarily need to go all the way to the end, if you came across a question that was like, what is the pH? When we got to the third table, did the hydrogen concentration change? No. When we were at the second hydrogen coming off, did it change? No. The majority of all the hydrogen that came off when? Very first step. And that's very common for diprotic or triprotic acids because, again, it gets harder every time you want to remove a hydrogen, which means if you have a different question than this where all you're interested in is the pH, just do the first table and calculate the pH off of that and you'll be fine. But if you have a problem like this where you have to get all the way down to phosphate, for example, you do have to go through all the tables to get there. By the way, we didn't calculate the pH here, but we could have if that was what we're looking for only as well. We'll put that in there, and that's going to give us a pH in this case of 0.71. Sounds acidic in this case. Any questions on diprotic, triprotic? Yes, sir. It really is. So majority of all, as you can see, I mean, basically in the second hydrogen, the first hydrogen we got off basically 0.194 molar, right? The second hydrogen that came off, essentially only 6.2 times 10 to minus 8 came off, right? And by the third one, it was like to the minus 19, so barely nothing wrote off. And it was too hard to do it. So the majority of that H plus that's floating around that solution is basically contributed by the first one that comes off. Other questions? And if you added them all together with all the, like to the minus 19s, it won't change the concentration as we saw at all. And it's going to be basically negligible, like you said. All right, that